So these are problems relating to work and energy, specifically the definition of work and the work-energy theorem. So the first problem here says, a boy pulls his sister a distance of 30 meters in a wagon by applying a force, 50 Newton force, at an angle of 30 degrees above the ground, and he's pulling against friction, right? So there's friction acting in the other direction. So the first question is, how much work does the boy do on his sister in the wagon? And then we're going to ask how much total work is done by all of the forces considered here. So we'll start by drawing a picture. So maybe here's a wagon, here's a little sister, and he applies a force here, so we'll call this FP, which was 50 newtons, at an angle of 30 degrees above the ground, so that's what that means. And there's some frictional force acting backwards. And he pulls this cart a distance delta x of 30 meters. Okay, so let's draw a free body diagram for this. So the free body diagram might look like this. It's y and the x. So clearly there's this pulling force acting here, so there's F pull. There's a frictional force acting backwards. And there's gravity, so there's F sub g, and there's a normal force. In fact, it's a little shorter than what I've drawn here. It doesn't really matter, because as you'll see in a minute, gravity and the normal force don't really play into this, this problem, specifically because they've given us the frictional force. Okay, so this angle here is 30 degrees, and we could label the x and y components of the pulling force here. So we'd like to calculate the work done, right? So we remember the definition of work. Work is the parallel component of a force times a displacement. Okay, so in this case we're calculating, for part A at least, the work done by the boy. So we just need the force that the boy is applying. Okay, but not all of this force is causing the wagon to move, right? Only the x component, only the part that is parallel to the direction of motion, right? So for the work done by the boy, it's simply the pulling force in the x direction times delta x. So I can fill that out. It looks like this should be 50 newtons times a cosine of 30 degrees times 30 meters. And if you do that math, you end up with 1,299 joules, or at 2 sig figs, 1,300 joules. So there's our answer for part A. Okay, so part B here asks how much work is done in total on the wagon and the sister. So that's going to include the work that the boy did and the work that friction does, right? So we could write that as the net work is equal to the work done by the boy plus the work done by friction. Alright, this is not the only way to do this problem, but I like to separate it this way because then we can think about friction by itself and then combine the two effects. So we want to know what work is done by friction. So it's simply going to be the frictional force, because it's all parallel, right, times delta x. But when we go to plug this in, we should recognize that the frictional force is acting to the left, and delta x is to the right. So the product of these two things should be negative. Okay? And that makes sense because the work done here should act to slow this object down, right? It's not actually doing work on the wagon. The wagon's doing work on friction. Or another way of thinking about it is that it's doing negative work because it's lowering the energy of the system. So we'll write that as minus 15 newtons times 30 meters, which gives us minus 450 joules. Alright, so when we go to calculate the net work, should simply be the sum of these two things, the work done by the boy plus the work done by friction. Work done by the boy was this 1300 joules, and the work done by friction is minus 450 joules, for a total of 850 joules. Okay, again, that makes sense. We're doing a difference here because only one of these forces is really acting in our favor. So now we can think about the second problem here. The second problem says calculate the average force that a sprinter exerts backward on a track to accelerate from 2 to 8 meters per second in a distance of 25 meters if he encounters a headwind that exerts an average force of 30 newtons against him. So let's draw this situation. We can draw a sprinter, or we can try. Maybe swing your arms a little bit, and maybe your knees are bent. Yeah, that looks like a sprinter. And here's maybe the ground. So then the forces that are acting here. So the sprinter pushes on the ground, right? So this is the force that the sprinter applies to the track. So we'll say sprinter on track, ST. And then the sprinter feels a force back, right? This is Newton's third law. There's a force of the track on the sprinter, right? So these are not both forces on the sprinter. This is the force on the sprinter, and the sprinter applies this force on the track. But they're the same magnitude, again, it's Newton's third law. And then there's another force, it's this headwind acting backwards. We'll call it F sub W. Okay. So let's draw a free body diagram for this so that it's a little more clear. Right, so the free body diagram, draw a y-axis, an x-axis, and let's ignore gravity. Well, let's not. We'll draw them here. We do have some gravity, F sub g. We have a normal force, F sub n. And then there are two forces in the x direction. One of them is the force that the track applies on the sprinter. So we'll call that F sub, I'm just going to call it F sub t. And then there's also this headwind, this wind force that acts backwards. So we'll call that F sub w. Alright, and again, we don't apply this force that the sprinter applies to the track because that's not a force on the sprinter, that's a force on the track. Okay, so this is our free body diagram, and now we can think about how does the work done by these forces affect the energy of the sprinter. Alright, and the way we investigate that is through the work energy theorem. So we can say the work done on the sprinter equals the change in the sprinter's energy. Okay, so we're going to need to fill out both sides of this equation. And then hope, or we'll hope that we can find the force from that. It's a little stronger than hope because we actually will be able to find it. So let's do the right-hand side first. The only energy that's changing here is kinetic, because we're changing velocities, but we're not changing height, so we're not changing potential, gravitational potential. There are also no springs, so we're not changing spring potential. So really all we have to do is this, K final minus K initial. Right, and now we can plug in, I'll write down the equations for each of these. For kinetic energy, it's half mv squared. Oops, minus. Okay, so I can plug in some numbers here. That's 1/2, 60 kilograms, 8 meters per second squared. Same thing, 2 meters per second squared. And if you do all of that, you end up with 1800 joules on the right-hand side. So that's the increase in the system's energy. And that's due to some work that's done by the net force on the sprinter. Alright, so we're going to write this, the work done is F parallel times delta x. Alright, and in this case we're asking for the total work done. Right, so we need the net force on the sprinter. So the net force on this sprinter is the force from the track minus the force from the wind, right, times a delta x. Right, and that makes sense. The force from the track is the response to him pushing on the track, and that's what speeds him up. And the wind is working against him, so that's going to come in with a negative sign. Right, so I can put in some numbers for this. I can say the, let's skip down one line, the force from the track minus the force from the wind is 30 newtons times 25 meters. Right, and if you solve this for the force from the track, you get 102 newtons. So you can see here that this 30 newton headwind, or the 30 newtons that he experiences from the wind, is actually significant, right? It's a third of the force that he's having to apply. So if there were no wind, he would only have to apply 72 newtons. So this is a significant amount of resistance from the wind. And that's an interesting part of this problem.